So the goal for today is to take some time to look back at what we've done and remind ourselves of all the wonderful things that we've learned. Wow! And of course, once we've done that, then we'll be ready if anybody should test us on our knowledge. So the very first thing, one of the very first things we talked about is the notion of verifying a differential equation. Now, of course, we might just remind ourselves, what is a differential equation? Well, an equation means that there's an equal sign, and so you have something equals something, and the moral here is that somewhere there's a derivative. And it might be more derivatives than, second derivative, third derivative, whatever. So there's one or more derivatives involved in the equation. So that's a differential equation. So how do you verify? Well, to verify means you plug it in. And so you say, okay, I have something which I think is true. And so what do? Well, I just check if I plug it in, does the equality hold? Okay, well, that's great. That doesn't seem very profound, but actually a lot of things that we do come off this idea of like, well, plug it in and see if it works. But there's also this notion of, well, we have this thing which we think might work. What do we do to see how to refine it? So you might have a differential equation, and we'll just make one up. Now, x squared y double prime minus 5xy prime plus 3y equals 0. And I say, okay, what's the solution? Well, it's not so clear from starting from scratch, but you say, oh, idea, make a guess. And y equals x to some unknown power r. And you plug it in, and that gives you an equation in r. And once you have that equation, you say, okay, this can work if you choose this value for r. And, or you might say, well, no value for r will work. And say, okay, great. Well, now we've learned something. It doesn't have that form. And so, plug it in. It's a wonderful tool. And we'll often use it. Now, another important idea is suppose that we have a collection of solutions. So we have a wonderful differential equation. It's linear, homogeneous. Now, what does that mean? Well, it means that our differential equation looks something like this. So there's some derivative, we'll say the nth derivative, and then there's some other pieces. Now, these other pieces don't have to be great in the coefficients. These can be really messy. But the punchline is that the way that the derivatives are set up is that they will be nice. So this is linear. Of course, it's not a differential equation because we don't have an equals. Equals 0. This 0 means homogeneous. And it says, all right, suppose you have this type of differential equation. Well, the linear tells us that there's this nice property. Linear means you can scale, you can add. So when we talk about linear combination, it says, oh, scale them by any number, add them together. And so we can do that. We can add this nice solution. Say, all right, well, if these were solutions, this is also a solution. And indeed, by choosing the y's carefully, all solutions will have that form. So in essence, when we have this linear differential equation, it says, okay, what are sort of our small collection of solutions? And then once we have them, then we say we have them all. Now, how do we know? Well, there's this notion of full. Okay, that's just a way of saying that if it's an nth order, and order here being, what's the highest derivative, and okay, linearly independent says that each one of them is contributing something new. In other words, there's no redundancy. Each one is useful. And that's a nice thing to have. That it's always nice to be useful, isn't it? So, all right, superposition, very useful, especially as we get into higher order differential equations. There's also this notion of a general solution versus a particular solution. Now, when we talk about general solutions to a differential equation, we basically say we want all possible solutions. And so when you're looking for that, say, well, you might need some constants. In fact, you will. So how many constants do you need? Well, if it's a highest derivative is an nth derivative, you'll need n constants. So if a first order single derivative, one constant. Second order, two derivatives, two constants, and so forth and so on. Now, how the constants show up are slightly different from what we may have seen in our first semester calculus. So for instance, the superposition, the constants show up in front of functions, not on the end. And that's all right. That's pretty typical. And in first order, oftentimes the constants can show up in some very interesting and perhaps peculiar spaces. But, well, that's part of the fun, isn't it? There's also the notion of particular solution. Now, particular solution says, look, I just need a solution. I don't need to worry about capturing all. I just need one. And sometimes one is all we need, something to help us get going. Now, a particular case of when you may want one solution is when you have initial value problems. So that is to say, I have a differential equation, and differential equations do what? They tell me how am I changing. Differential equations are about change. Derivatives are about change. Initial value says, where am I at the start? So if you combine those two pieces of information, where am I at the start with how am I changing, you should be able to say where you are. Just follow it along. And that's what we call the solution. That's kind of the goal of differential equations, is to be able to answer questions like that. Okay, so when we have our initial value problems, then we're looking for the solution, a particular solution, which it both satisfies the differential equation and satisfies the initial condition. Now, what do? Well, what the approach is first off, find the general solution. You have a bunch of constants, maybe just one, and then say, okay, given my initial condition, plug in your initial condition or conditions and say, okay, what does that tell me about my constants? And then you can solve, and then you have the one, the solution that you're looking for. So now we're up to getting our hands more and let's actually talk about how do we solve them. We've been talking a little bit about here are some basic underlying ideas, but let's get our hands in and say, okay, what do we do? And we'll start by talking about first order differential equations. Now, first order differential equations means there's a single derivative. So in essence, we say, well, look, we just have to do some integral, right? Because if you have one derivative, you integrate, life is good. Well, of course, the problem is when we have both the derivative of the function and pieces of the function showing up, it's not quite that easy. But there are some cases where we can make progress and actually solve. There's three in particular. The first kind is separable. Now, separable differential equations have a very particular form. They look like y prime equals, and we have stuff with x and stuff with y multiplied together. And I know stuff is not a very technical math term, but you get the idea, right? And I should add another thing, of course, is when we talk about x and y, there's nothing sacred about these symbols. It's just convention. And oftentimes we might switch and say, oh, x and t, or y and t, or p and t. And, there's lots of different options. We're just using y and x generically. So a separable differential equation is something that can be put into this form. All right, so that's why there it says it usually involves lots of multiplication. That's what we're talking about, multiplying these pieces together. So what do? Well, the name kind of gives it away. Separable relates to separate. So you say, okay, when you think about y prime, it's Sometimes, in fact, often when you're in first derivative case, it's convenient to think dy dx. So, all right, move the y's to one side, x's to another side, and now you have two sides. You say, well, this quantity equals that quantity. So, all right, great. So now integrate both sides. You say, okay, well, if I have two things which are equal, then if you integrate the two things, they're still equal up to a plus c. So there's 1 plus c on one of the sides. You don't need two. Now you've done the hard part. You've gotten rid of the derivative inside the differential equation. And so the last thing is to uncomplicate. Well, that's just a fun word. So you have the 8, 8, 8, right? And, well, that means solve for your function and or constant. Sometimes you can't solve for your function. It happens. That's okay. And you can usually solve for a constant. And so how do you do that? Of course, plug in initial conditions. All right, well, as we move on, there's another type of differential equation, linear. Now, linear here is the same kind of linear we just talked about. So you look at how the y prime and y are related. You just sort of, if you see a formula and you say there's a single y prime and a single y, and everything else is the other variable, like almost surely linear. So you say, okay, so y prime plus something times y equals something. Great. Well, what do? Well, of course, the mantra is the same as before. We're trying to integrate, find a derivative. So what we do is we find an integrating factor. Now, what is the idea? The real goal is to say, I can make one of these two sides a derivative. And really, it's this left-hand side that we're after. The reason we're after the left-hand side is because the left-hand side is the tricky part. It involves the y terms. So if we can make the y parts easy to integrate, then we win. So you find this expression, the integral of this coefficient p of x dx, and take e to that. And if you do it right, of course, be careful. And when I say be careful, double check, what's in front of the y prime. It's better be a 1. If it's not, make it a 1. But all right, if you do that, you multiply through, then the left-hand side, by design, guaranteed, 100%, it's a derivative. Namely, it's the derivative of the integrating factor times y. All right, great. So what does that tell you? Well, it says, look, you have this wonderful thing going on. The derivative of the integrating factor times y is the integrating factor times q of x. That's easy to integrate, and that is something, but it doesn't involve y. And so we say, okay, well, that could probably be integrated too, and life is good. And off we go. All right, so good. So that's the idea. Integrate, and you've got your solution. The third thing that we can do is something called exact. Now, exact has a very particular form. And now any first-order differential equation can get to this point, theoretically. But what do you have? Something, so I'm thinking of m as a function, could involve x and y, dx, plus something, dy. And usually m and n, hopeless. All right, well, that's not enough for exact. There's this sort of underlying thing that goes on that says, actually, these pieces m and n aren't just random, but they come from a common source. There's this, here's m and n. Somewhere floating up here is a function that they both came from. And so that doesn't always happen. So not everything that has this form is exact, but usually if you see this form on, say, a test, then it usually is. And so the goal is to say, okay, find this big overarching thing. So what do? Well, the idea is this part really is a derivative with respect to x, and this part's a derivative with respect to y. So you integrate them respectively with respect to x and with respect to y, Say, okay, here are sort of two snapshots of my big thing. And now, you say, all right, are they compatible? Well, the relevant parts here, we talk about the relevant parts, those are parts that have both x and y. They have to overlap. So if they don't, it's not going to work. But if they do, life is good. Because what happens next, say, all right, now I can take my two snapshots, my two perspectives on my function I'm after, and piece them together. And so you say, well, I can see the overlap, the just x, just y, and now I have all of them, and that equal to some arbitrary constant is the solution. So these tend to be implicit. And so if you see the word implicit, it's very likely exact. All right, so those are our three approaches. And the nice thing, of course, is with first order, we have a little bit more flexibility. You'll see once we talk about second order, it gets a little bit more restrictive and there's not as many options. Now there is one other thing that can happen, and this isn't really about solving the differential equation, but rather it's about simplifying. A lot of math boils down in the end to saying, look, this is hard. Can I make it easier? And if you can, do it. Make it a little bit easier, a little bit easier. And if you keep doing that often enough, all of a sudden, life is good. It's just right. And we're able to succeed. So what's the idea? It's like Calc 1. The idea is to say, okay, can I replace the variable I'm trying to solve in the differential equation, the part with the derivative, with a new variable in such a way that the new differential equation is a little bit easier to work with. And so if you channel your inner Calc 1, our young, innocent child self, and say, okay, well, you look for things that are on the inside, or you look for easy derivatives. There's not that many things that can happen. But there's, in theory, of course, many, many things can happen. But in principle, only a few things happen. So there's three kinds of substitutions that we really want you to be able to do. The first one is what we call homogeneous, which is unfortunately an inconvenient name because we've already said homogeneous to mean something very different, but, well, unfortunately we started recycling, and so it is what it is. And what we mean by homogeneous is really, here we write it as y is u times x, where u is some unknown function. We should really say, well, it really comes from saying, I can write everything in terms of this expression y over x, and then, all right, replace all the y over x's by this new variable. Don't forget, not only do you have to replace y, you also have to replace y prime. So that's the important thing. So that's why it writes it as y equals ux, because you have, y prime is u times derivative of x is 1 plus u prime x. All right, Bernoulli. Now, Bernoulli, it's kind of fun because what do you have? It says, if you have something that looks like this, y prime plus p of xy is equal to q of x, y to some power. I'll put power n here. That's Bernoulli. And you might say, well, wait, hold on. Isn't that linear? Well, it would be linear if we covered up that part on the end. But when we add that part, unfortunately, we no longer just have y prime and y, we have this extra piece. But the nice thing is, by rewriting it, and by rewriting I mean divide it out by y to the n, there'll be a nice substitution of the form y to some power. And of course, we also have to replace the derivative, but in that case, it's not hard to see that u prime is equal to k y to the power of k minus 1 y prime. And that's what we do to replace. All right, so homogeneous, Bernoulli, and of course, the third thing we want you to be able to do is follow instructions. In other words, we say, okay, look, we're just going to hand it to you. it takes time to develop skills, and oftentimes there's a good substitution which can be very difficult to spot. It's not easy to learn, but the process is more or less straightforward. You say, look, replace all the variables, including the derivative, and that's what you do. And so if something's given to you, you just don't put a lot of thought into it. Say, all I have to do is update it, so I get rid of my old variable, and everything's in terms of my new variable, and life is good. And a good substitution will open it up to separable or linear. Exact, honestly, unless you start exact, it's hard to get to exact. And so it is kind of, you're either in or you're out. You know, you're either exact or it's hopeless. You're not going to make much progress. You might say, but wait, isn't there in theory a way that you can make something exact if it's not? In theory, yes. In practice, forget about it. It's not going to happen. So these are your two main ones that you're after. So now that we can actually start solving differential equations, at least we talked a little bit about first order differential equations, we can also start getting to things such as, what are some applications, things that we can do with these? There's going to be more or less three varieties of problems. Well, the first kind, population. But really, when we talk about population, it's all about growth. So anything that can grow over time is population. Now, of course, I guess I shouldn't say just growth is positive. You can have negative growth. Things like exponential decay also fall into these types of models. Now, there's two main ones that you will encounter. One is what's called the exponential model, which says that the derivative is proportional to, that's the k, of what we currently have. And why do we call it exponential? Well, because the solution looks like an exponential function. There's also the logistic model, which is a little bit more fancy. P prime equals, again, proportional to, there's some constant p, but then there's this extra factor m minus p. Now the thing is that when we talk about the exponential model, it has exponential growth, very unrealistic because there's environmental factors. With the logistic model, yeah, there's growth, but then you start hitting environmental factors and it levels off. And this sort of leveling off point is that where m is. And m is, you can think of as the carrying capacity. It's just how much the environment can support. Now, of course, I said these are the two main ones. There's other ones that can be used. But for those other ones, more or less, we just solve them as they come. And now, what do we do? What might we expect? Well, on exams, they might say, do we understand what things represent and how to use them? And in particular, we love to play with the logistic model. Just say, okay, I'll give you a little piece of information. Can you find another little piece of information? But the nice thing is, we actually have an explicit solution for the logistic model. Of course, we can all say it together, right? P equals, right? It's m p0 divided by p0 plus m minus p0 e to the minus kmt. Exactly. We all got it. Good. Now, no, you don't have to memorize this. You will have it given to you. And, but, we understand how things behave. All right, so that's growth, first derivative. Another problem is mixing. And this is almost always phrased in terms of there's a tank. So you have some sort of tank, you have something coming in, and you have something going out. And so you have inflow, outflow, you have some substance, usually salt. It doesn't have to be. Sugar, if you like things to be a little bit sweet, and you're like, these problems are too salty. All right, we'll make it about sugar. And then you're like, oh, sweet. And so you have to say, all right, well, what happens? Well, you say, okay, if I want to understand change, well, if it's salt, salt can only come in from the outside, and it can only leave from the inside, right? So I have something coming in, something going out. So the change, we just have to say, okay, change, look at how is it coming in, how is it going out. That sets up a differential equation. And you say, all right, once you have your differential equation, you can solve. And almost always in this particular setting, you're going to end up with what's a linear first order differential equation. And so this is a good way to sort of combine those two. Linear first order plus word problems. Don't we love word problems? Yeah, that's why we like to say word problems are great. So that's the second type. The third type, and that's a second order differential equation type problem, is springs. And really we just use springs as our underlying example, but it's not just about springs. It's really anything that has to do with vibration. And lots of things vibrate. And how does it behave? Well, you have mx double prime, mass times acceleration, force. Then you have c, which is called the damping constant, times velocity. And then you have k, which is spring constant x. Now you might say kx, that sounds like Hooke's law. Because it is. That's Hooke's law. And then you may have some external force. Usually it's 0. And now you say, okay, well, there's not really much of a picture, right? Because a spring looks like a spring. But you say, well, what are m, c, and k? And sometimes they'll give you two of them and say, what can you say about the third? They'll also ask questions about what's the behavior. Now, we haven't quite gotten to how we solve second order differential equations, but when we do, we'll see that it boils down to understanding the roots of a certain polynomial, namely the polynomial mr squared plus cr plus k equals 0. You're like, oh, that looks suspiciously like those coefficients. Yes, yes. And, well, when you write down the roots using the quadratic formula, you get the following expression, and it all boils down to what's inside the square root. And it turns out that a couple things are true. So if what's inside the square root is negative, you get complex numbers. And complex numbers in differential equations don't mean, aha, we throw up our hands and hopeless, hopeless. No, no, no. Complex numbers mean, oh, vibration, sines and cosines. Because, springs should behave like sines and cosines. So that would be, so complex numbers will tend to be what we call underdamped. If the c squared minus 4mk is real numbers, the square root of it, in other words, the c squared minus 4mk is positive, we'll end up with distinct row roots. And then in that case, our spring won't look like a spring. It'll be like, And that really is saying that the damper is so powerful, it overwhelms the spring, and sort of you have a slow return to normal. And of course, there's that sweet spot right in between called critical damping, which is the best, right? So why would we call it critical if it wasn't the best? But there we go. 3 flavors of word problems. And, probably should expect to be able to see one or more of these somewhere on the exam. If there is one, right? So we talked about solving first order differential equations, and we talked about applications, but realistically, there are a lot of things that are just hopeless for us. We just can't get an explicit answer. But even when we can't get an explicit answer, we can get kind of a qualitative answer. We can say, look, we can say some things about it. And an example of this are what are known as autonomous differential equations. Something in the form y prime equals f of y. And what can we do? Well, we put on our Calc 1 hats and say, let's channel the first derivative test. And we say, okay, well, what are some things? Well, you want to know the critical points. Well, okay, Calc 1, where does the derivative equal 0? That's f of y equals 0. Now, why do we like that? Those correspond to constant solutions. In other words, really easy solutions. And now you say, all right, well, I can continue channeling my inner calc 1, and I can say I have the line, so here are my y values, and I can mark the critical points, and so maybe I have these critical points, and we just make up some numbers here, -3, 1, and 7. And now what can we do? Well, what we can do is we say, what's happening with y prime in between? Because we can plug in. And you say, well, maybe here y prime is positive, and maybe it stays positive, but then it switches to negative, and then it's back to positive. Maybe. Yeah, there's something that does that. Say, okay, great. Well, what's going on? To say y prime is positive says, hey, I'm going up. So y is increasing. So when you think about left-right, positive means to the right, to the right. So it says if you're below -3, you should go up towards -3. Notice it matches the inequality sign. Coincidence? Yes! But that's okay! Well, let's enjoy it. All right, so where we see positive, we're heading up. Where we see negative, we're heading down. So we're going the other direction. And so we say, okay, great. Well, how do we put it all together? Well, now we look at behavior. So where I have a point where things come in, then that is something that we'll call stable. It says, look, if you're here, if you are slightly off, then you want to move in. Maybe you're slightly off, you still want to move in. If, on the other hand, I have a point where if I move a little bit off, then I head away, and it's true on both sides, this is what we call unstable. So things move away from your critical point. And then, of course, you can have sort of half and half. And so for that, we call it semi-stable. And that's the three cases, three categories. So this part right here is the phase diagram, and then we have the classification. And it also helps us say, okay, we talked about qualitative. One thing that we can say is, what's the long-term behavior? So for instance, suppose I say I start at some time at y, my y value is 5, so I'm here. What happens? Well, if my y value is 5, well, I follow the arrow, and in the long run, I go to 1. And that's it. If I start out at -5, I head up towards -3. I don't cross it, because I'm only going to get closer to it. But again, once I know my initial y value, I know where I'm going to end up. So this is an example of a case where we can actually say something interesting about, we know what the behavior could be, even if we don't know what the explicit solution is. So now we can move into higher order differential equations. Let's start with our favorite kind. Constant coefficient, linear, homogeneous. Nice! These are our favorite kind of differential equations. Why? Because there's a wonderful way to approach it. There's this, essentially, you've probably seen me draw this before, but you have 4 corners of a square. You have an ODE problem, an algebra problem, and then you have an algebra solution, and you have an ODE solution. And, well, of course, we're starting with a differential equation problem. We want to get to our differential equation solution. So ideally, we're trying to do this. And we say, well, actually, we're going to change it into algebra, use our algebra tools to solve, and then interpret our algebra answer into a differential equation answer. And so how does this work? Well, what we do is we say we can turn a differential equation into a polynomial. And sort of the underlying idea behind all this is we say, oh, this really, we're guessing that y looks like e to the rx for some choice of r, and this gives restrictions on what r values will work. Now, if it's an nth order differential equation, there's n possible choices choices for r, which means there's n roots. And each root gives a solution, and if we're careful, we'll get n linearly independent solutions, which means after superposition, we have it all. Wow. Great. So we just need to find how do the roots become solutions, and then of course at the very end, don't forget, we're going to have superposition, and that's going to give us our full answer at the end. All right, so what do we do? Well, we said our roots look like e to the rx. So there's, in some sense, it's trivial, but there's two subtleties. So let's talk about them. Subtlety one, what if we have repeated roots? Because I can't have, e to the x and e to the x and e to the x, because they're not distinct. They're the same function. So when I have repeated roots, there has to be a way to sort of modify each subsequent one. And we're not going to change the upstairs. So we're not going to change the rx part upstairs. What we do is we add factors of x in the front. So we'll start with, say, e to the x, and it's x, e to the x, and it's x squared, e to the x, and we work our way up until we've gotten our k functions. I like to call this bump. And so it just says, look, if you have repetition, you have to somehow get to the point that says, oh, you actually can turn that into a collection of functions by adding the factors of x. There's a reason why it does work, and if you watch one of the earlier videos, we go through and explain why it works that way. So that's how you handle repetition. What about complex? The second thing that might happen. Well, again, it's still true. You could put r as a complex number, and that's technically perfectly valid. However, it just feels weird. We're so used to what we call the real world that when we see imaginary numbers, like, ugh, but there's really not that much going on with imaginary numbers. They're perfectly fine numbers, and the key here is that there's this beautiful fact that if you look at e to the I theta, that's cosine theta plus I sine theta. And so it turns out, if you apply this, you say, well, if your roots look like alpha plus minus beta I, well, the real part still behaves like we think it should. Still behaves like this exponential. And then the imaginary part, it's going into a cosine sine. And because these come in pairs, and they will come in pairs as long as we have our roots, our real numbers, then we say, oh, these solutions come in pairs. Then, of course, if we have repetition, we do what we did before and add powers of x. So there we go. So now we know how to turn it into an algebra problem. We can talk about finding the roots, and we know how to turn our roots back into solutions. We use superposition. Life is good. This is one of our favorite types of differential equation problems because we love algebra. Algebra, yes. All right, good. Now we keep talking about superposition so much because when it comes to higher order differential equations, the only kind we like to talk about are linear because they're the ones we can make progress on. So how do you solve a generic linear differential equation? Well, there's a process. And what's going on is that our solution, you can write it as two pieces. So yc plus yp. And there's the complementary part and the particular part. So let's talk about how we find these pieces. Well, the complementary part says make it homogeneous. Homogeneous has some nice features into it. And namely, this is where the superposition really comes in. And it says, all right, you replace f of x by 0. You find your solutions in some way. Oftentimes, when we actually find these, it'll be a case where we have constant coefficients, and we just talked about how to do that. And say, all right, now we can use any combination of this. And so we have our complementary solution looks like c1y1 up to cn yn. Now, That's the YC, complementary. YP, well, YP is particular. Now, what does the particular solution do? Well, the goal of the particular solution is to really say, here is a solution. Just one solution which gets the f of x. Now, you say, all right, what can you do? Well, you can add them together. And the two parts serve purposes. So the YP, this part handles the f of x. So you say, all right, that's great. What does this part handle then? Well, this part, it handles, in some sense, I'll phrase it as initial conditions. But really the important thing here is it shows you that you get all possible solutions. And so, between the two of them, we have everything covered. We solve the differential equation, and we can cover any possible set of initial conditions. We have the general solution. So there's something that might happen, which is, well, what if you do have initial conditions? Well, if you do, then you use the full part, not just the complementary part, but everything together, and you plug in and solve for initial conditions as needed. And there we go. That's the idea. But of course, there's the question, how do you actually solve for that particular solution? How do you find y sub p? All right, so there's two things that we're going to talk about. Method 1. This is the method of undetermined coefficients. And again, our goal here is to find y sub p. And what are we after? Well, what we have is a very nice differential equation. On the left-hand side, constant coefficient linear. The right-hand side, the f of x part, the f of x part is also nice. It comes out of a constant coefficient linear homogeneous differential equation. And in particular, the f of x, the pieces have a very particular shape, right? They look like x to some power e to ax cosine bx, or x to some power e to some power sine of bx. Now, of course, you may not have the trig part, you may not have the exponential part, you may not have the x to the power part. There are any combination of those. But those are what the parts look like. And if the parts don't look like that, forget it. Hopeless, hopeless. So, what's the approach? Well, you start by finding yc, because that's going to be important. And then there's a second part. And I like to call this now, making a list. Because it's nice to think about making a list. There's even a song about, we're making a list, checking it twice, gonna find out which pieces are nice to include in y sub p. All right, so how do you make the list? Well, first thing is you have to sort of fill up the list with some initial parts. So you put in the parts of f of x. Great. That's what this thing is. Now, you say, okay, check to lower powers of x. And, okay, in other words, if I have like x squared, I better have x, I better have 1. If I have x squared e to the 2x, I better have x e to the 2x and e to the 2x, and so forth and so on. Then, I check to make sure sine and cosine always has pairs. And so, for example, if I have a sine 2x in my list, I have to have a cosine 2x in my list. And similarly, if I have e to the 3x sine 4x, I have to have e to the 3x cosine 4x. And you keep it going. By the way, when we talk about the parts of f of x, we only want the functions. Don't worry about the constants. And now, this last point, when you're making your list, is avoid overlap. And so here, in some sense, once you've reached this stage, you have the right parts, at least the right number of parts. The only issue is, well, wait, what if some of the pieces we put into YC and it disappeared? Well, if we did, well, that's bad. We want to make sure that nothing disappears when we plug it in to the homogeneous part. And so we say, okay, if something were to disappear, we bump it up, and you have to bump up whatever's in the same family. So in other words, you know, okay, watch the video, right? Yes, watch the video, and we'll get into that. All right, now that you have your list, you're basically done. What do? Well, I shouldn't say you're basically done. You're halfway done. The next thing is to say, I know what YP looks like. It's a particular combination, or if you like, it's a particular superposition. So Y sub P is a particular, not an arbitrary one, but a particular superposition of our list. And we say, okay, so what's the problem? Well, the coefficients matter. They have to be very specific numbers. And so right now, the coefficients aren't determined, and hence, method of undetermined coefficients. So how do we determine them? Well, we go and channel our verify. We plug it into the differential equation, work it all out, and then start comparing coefficients and say, oh, I need to have 8a needs to equal 16 or something. Oh, a equals 2. And you just do it. Well, function by time, function on the left, I'll group everything. Function on the right, group everything, and just compare coefficients. And it sets it up, and it lets you solve. And so it can be a little bit time-consuming, but the underlying ideas aren't bad. Just practice. So practice, practice, practice. There will be a second approach to finding Y sub P, but before we can talk about it, we need to step back and mention the Wronskian. So the Wronskian is a way to test whether functions are linearly independent. In other words, hey, are these really different functions, or are they the same function masquerading as each other? So how do you do it? Well, if you have two functions, you set up a 2 by 2 matrix. And in the first row are the functions. And in the second row are the derivatives of the functions. And then you take the determinant. Now, that is to say, we're going to take diagonals. So y1, y2 prime, subtract y1 prime, y2. And now we look at this and say, okay, what's this value? And we care about really 0 versus non-zero. If it's always 0, they're really the same function. And you say, great, I haven't learned anything by adding in this second function from the first. If it's non-zero, they're different functions. And the nice thing is, when the Wronskian is non-zero, you can always solve for initial conditions. When the Wronskian is 0, you can't always solve. And so something starts to break down in solutions. So essentially, your solutions will be good when you have a linear homogeneous differential equation. They're going to work up until the Wronskian vanishes. And at that point, all bets are off. So we talked about saying there's two ways to find a particular solution, and this is our second way. So again, our goal here is to find Y sub P. And here's the setup. We are a second order, so we're narrowing our focus down. Differential equation, we're linear, but we are more flexible. Whereas in the method of undetermined coefficients, our left-hand side had to have constant coefficient. This doesn't. These can be functions. And the right-hand side had to be nice. This does not have to be nice. So it's more powerful. But with great power comes great need to do more work. And so this can be a more challenging technique. Ergo, if you can use undetermined coefficients, use it. If you can't, well, then you have an option. And the basic process is outlined here, but the punchline here is you have a differential equation. You want to make sure that's what's in front of the y double prime is 1. And we have the solutions to the homogeneous portion. In other words, if you look at y double prime plus p of x y prime plus q of x y equals 0, then your solutions look like some constant y1 plus some constant y2. Well, we're going to build off of these. So we build off of saying, hey, we know about y1, y2. Can we get to a particular solution? And the punchline is to say, well, yes, you can. And now, whereas a and b were constants, we say, well, throw in some functions. And now you just have to find u1 and u2. And there's a process, you carry it out, and at the end of the process, we're skipping the details. You can always go back and watch the video. You get this lovely, lengthy formula. Now, this might look scary, but the thing is, it's a formula. We don't ask you to memorize it. You can understand sort of the process to get there, but really it's just a method, right? Say, look, what are my pieces here? Well, there's the y1 and the y2 and the Wronskian and the f. And just have to know how to plug your pieces in, and you just carefully work it through. And there you get your answers. Whew, wow. What a journey we've been on in these last, however long, let's say a couple weeks. And it's been great. Maybe it's time for us to really test ourselves to see how well we've learned. So we have lots more coming up in the future, so I hope to see you back. But in the meantime, be good to yourselves and take care. Bye.